Ever pondered why time ticks slower in space than on Earth? It's a query that stirs the mind and challenges our understanding of reality. It's a question about time and space, and it's not as far-fetched as you might think. You see, astronauts experience this phenomenon, known as time dilation. Yes, time really does move slower for them while they're in space. It's not science fiction, it's actual science. Intriguing, isn't it? Let's delve deeper into the mystery of time and space. Our understanding of time and space owes much to a man named Albert Einstein. A physicist born in the late 19th century, Einstein's remarkable intellect led him to contribute significantly to the field of theoretical physics. His most influential work, without a doubt, is the theory of relativity. This theory is, in essence, a two-part symphony of understanding. The first movement, if you will, is the special theory of relativity. It came to Einstein in 1905, and it fundamentally altered our conception of space and time. In layman's terms, it tells us that the laws of physics are the same for all non-accelerating observers, and that the speed of light within a vacuum is the same, no matter the speed at which the observer travels. This means that time can appear to move slower for a moving object compared to a stationary one, a phenomenon known as time dilation. The second movement of Einstein's theory, the general theory of relativity, came a decade later. This part of the theory is a little more complex. It posits that massive objects cause a distortion in space-time, which is felt as gravity. Imagine, if you will, a heavy ball placed in the middle of a stretched rubber sheet. The ball would cause a dip, a curve in the sheet. That's essentially what massive objects like the Earth do to the fabric of space-time. Now, a key point to remember is that these theories are not just abstract academic ideas. They have real-world implications that affect us every day. For instance, the Global Positioning System, or GPS, that many of us rely on for navigation, would not function accurately without accounting for the principles of relativity. Einstein's theory revolutionized our understanding of the universe, but how does it explain time dilation? Time dilation, a mind-bending concept, yet a proven fact. Now let's dive into the nitty-gritty of time dilation. Imagine for a moment that you're aboard a spaceship, traveling near the speed of light. Back on Earth, your loved ones are going about their daily lives. But here's the kicker. While you might experience only a few years of travel, decades could pass on Earth. This is a direct result of time dilation. But how does this work? Well, let's use a simple analogy. Picture time as a river, flowing steadily. Now, if you were to speed up, it's as though you're rowing against the current. The faster you go, the harder it becomes to move forward, slowing your progress. This is somewhat similar to how time behaves at high speeds. The faster you move, the slower time appears to pass for you compared to a stationary observer. Now let's introduce gravity into the mix. Imagine a trampoline. If you place a heavy object in the middle, it creates a dip or a curve. Similarly, massive objects like planets and stars curve the fabric of space-time around them. The stronger the gravity, the more pronounced this curve, and the slower time moves. This means that time passes more slowly for someone at sea level, where gravity is stronger, than for someone at the top of a mountain. So, you see, time is not the unchanging, unyielding entity we often imagine it to be. It's more like a flexible fabric, stretching and contracting based on the forces acting upon it. Time dilation, in essence, is the result of these alterations in the flow of time caused by speed and gravity. But wait, you might ask, is this just theory or is it reality? Well, it's as real as the device you're using to watch this video. GPS satellites, for instance, have to account for time dilation, or they wouldn't be able to provide accurate positioning. So as we can see, time isn't as straightforward as it seems. But how does time dilation work in real life, you might be asking? Well, it's not as abstract as it may initially sound. In fact, it's integral to some technologies we use every day. Take our Global Positioning System, or GPS, for instance. These satellites orbiting the Earth are moving at high speeds relative to us on the ground. According to Einstein's theory of relativity, time should tick slower for objects in motion, so these satellites experience time dilation, their internal clocks ticking ever so slightly slower than ours here on Earth. But surely, you might think, such a minuscule difference doesn't matter. On the contrary, it matters greatly. If not accounted for, the GPS signal's time discrepancy would cause inaccuracies in location data. Imagine your GPS telling you that you're 5 miles away from your current location. That would be quite a pickle, wouldn't it? Therefore, these satellites are programmed to adjust for this time difference, ensuring the data they relay is accurate. Now let's take a more human example. Astronauts, when they're zipping around in space at high speeds, they too experience time dilation. Although the difference is incredibly small, an astronaut on a 6-month mission on the International Space Station would age less than those of us on Earth by about 0.007 seconds. So when they return to Earth, they're technically a smidgen younger than they would have been if they'd stayed home. It's not enough to notice, of course, but it's a fascinating demonstration of time dilation in action. These examples show that time dilation isn't some far-off scientific concept only relevant in the realm of black holes and light-speed travel. It's a tangible phenomenon that engineers and scientists must account for in our everyday technologies and space explorations. So, time dilation isn't just theoretical, it's a part of our everyday life. The theory of relativity and time dilation have profound implications. Dive with me now into the depths of these implications as we unravel the fabric of our understanding of the universe and our place within it. The theory of relativity, with its groundbreaking concepts, has transformed our perception of time and space. No longer are they rigid, unchanging entities, but fluid and dynamic aspects of our reality, intertwined in a cosmic dance. Time dilation, an intriguing byproduct of relativity, has opened our eyes to the fact that time, as we perceive it, is not universal. It's like a river, flowing at different speeds for different observers, influenced by the gravitational pull and the velocity of their movement. This realization has far-reaching implications, altering our understanding of age, travel, and even the nature of existence itself. The potential for future discoveries and advancements in this field is simply staggering. Imagine, if you will, a future where we can manipulate time dilation to our advantage. Could we then outlive civilizations, witness the birth and death of stars, or even travel to distant galaxies within a human lifespan? Furthermore, the theory of relativity has pushed us to question the very nature of our universe. It has led us to the concept of a multiverse, where countless universes exist in parallel to our own, each with its own set of physical laws. This could mean that there are universes out there where time dilation and relativity do not even exist, or perhaps work in ways we can't even begin to fathom. And remember, these theories are not mere philosophical musings. They have tangible effects on our everyday life. For example, the GPS technology that we rely on daily would not work correctly without taking into account the effects of relativity and time dilation. As we press forward in our quest for knowledge, these theories continue to challenge our understanding and push the boundaries of our curiosity. They are testaments to the infinite possibilities that lie within the realm of science. It's clear that our understanding of time and space will continue to evolve. Time dilation and the theory of relativity can be complex, but they're essential to our understanding of the universe. We've delved into the riveting world of space-time, journeyed through Einstein's groundbreaking theory of relativity, and unlocked the enigma of time dilation. We began with a question of time and space, a fascinating mystery that has intrigued scientists and philosophers for centuries. Our exploration took us to Albert Einstein, the genius who dared to challenge the conventional understanding of the universe. His theory of relativity revolutionized our perception of space and time, intertwining them into the inseparable fabric of space-time. Our journey didn't stop there. We ventured further into the realm of time dilation, a mind-bending concept that time can stretch and contract based on speed and gravity. We saw it in practice, from the atomic clocks on satellites ticking slower than those on Earth, to the hypothetical space traveler aging less than their stay-at-home twin. We also touched on the profound implications of these concepts. They've shaped our understanding of the universe, underpinning technologies like GPS and opening up fascinating possibilities for space travel and understanding the cosmos. The universe, as we've come to understand it, is a wondrous place where time and space dance to the rhythm of relativity. The next time you look at your watch, remember, time isn't ticking at the same rate everywhere in the universe.